can fill in here for our scatter plot argument. So Nancy says X equals iris features I, Y equals iris features J. Something like that. That's very close. I think you're definitely on the right track. We need to like pick out the right columns. But for example, if we just call one number, so we look at iris features, and let's say I is 1, right? Because that's like the first like iteration in our loop. We call iris features 1. That's just a row. Because again, if we look at iris features as a whole, you can see that this array corresponds to this element in our array. So if we just call iris features I, then we're just going to get rows. There's another way that we can do it. Because iris features it's a two-dimensional array. We have a bunch of rows, and each row has elements in it. So we can do, instead of I or 1 or whatever, we say we want all rows, use the colon. You may have seen that before, like very similar to kind of like dot lock notation for pandas. And then we want only a specific column. So if we want only the first column, we can do that. Or this, I guess this would be the second column. We can do that, and then this looks a lot more like our column. And then we can see, we can verify that. We can just check the first field values, 5.1, 4.9, 4.7, 4.6. So this is how we access a column. So we can do that, and we can go, oops, again, I'm poor at that. So we want the ith column, and then we want the jth column. If we want to be explicit about it, we can say X and Y. And then what do we think goes, what's our hue? Says use the hue argument to color points by class. If we don't use the hue argument, then we get something like this. So clearly, we've drawn the scatter plots appropriately. We see sepal width, sepal length, petal length. Like these are clearly nice looking scatter plots here. We have a couple of suggestions. Hue equals iris target or iris target names. I guess we can just look at both of them. So if you look at, say, iris target names, that's just literally an array of the names. So if we feed that into here, that's probably not going to, that's like iris target names alone isn't going to tell us which point is in which class. So we can look at iris target, and then we see, great. For each point, it looks like each of these elements in this array corresponds to each point. So then we can do hue equals iris target. And then now we see a whole bunch of different scatter plots, which is kind of cool. This is a scatter matrix. So yeah, we can look and we can see different combinations of features where each of the classes fall. Any questions about question 1?
Could you go back to the code for just a second?
The code, this code?
Yes, just for 5 seconds.
Yeah. So I think the tricky parts here are knowing how to extract columns from like a 2D NumPy array. Normally we just use data frames, which makes our lives easier, but in this case we didn't. So it's knowing how to do that. Obviously setting the hue, and then all this other stuff that they already gave us is important to kind of recognize too, like following the logic of how they iterate through and draw the scatter plots. All good, Evan? Okay.
Yeah. Okay. Okay. Thank you. Yeah.
All right, sounds good. So this is just plotting. Doesn't really have anything to do with PCA, like on its own. But you can kind of see like you're like maybe you want to like imagine like some clustering, and you can say, oh, like which of these combinations of features like best determine like what type of flower is each point. Um, but whatever, that's all fine and dandy. So we move on to question 2. So it says to apply PCA, we first need to center the data so that the mean of each feature is 0. So it says compute the column-wise mean of iris features. So again, that's our 2D array. In the cell below and stored in iris mean should be a NumPy array of 4 means. Then subtract iris mean, great. So it says hints, use np.mean. Okay. So I guess the first thing I want to do is I'll just call np.mean on iris features. And I just get one number. So that's not super helpful. This is looking at every single every single element in our array. So yes, a couple people in the chat are saying add in the axis equals 0 argument. And if we do that, now we see something exactly like we should. 4 values in our array. Something else, if you were thinking like, well, if we do axis equals 1, then this would be like the row average. So these are the row averages, which we don't want. We want axis equals 0. Thank you to those in the chat. So we can go ahead and assign this to iris mean. So that's great. But then now we have to subtract this mean from all of our different values. So this one is actually like very straightforward. So what we can do is we can do just our iris features. Like the first thing you might try is iris features minus iris mean, which I'll just copy here. And it looks like that actually works. We still maintain, like our array still has the same shape, but it definitely looks like we subtracted the right values from like the right positions. Question in the chat, axis equals 0 takes the average of each column. Yes. Axis equals 1 would take the average of each row, and axis equals, like, we didn't define axis at all, then it's just the average of all the values. This is just one number. So yeah, so like now we have to subtract this mean from our overall big feature data set. So again, the first thing you might try is this, and this actually works. You can read more about like why this works and with this link about broadcasting. But in this case, it's very easy. We don't need to like specify any extra axis arguments or whatever. A lot of times NumPy and pandas can be very confusing in terms of like, how do I do what operations in which way? In this case, it's super easy. So we can just do iris features minus iris mean. And then again, you see it just displays iris mean. And then do we pass the test cases? Yes, we do. Any questions about 2A before we move on?
Why is axis equal to 0 and not 1?
Sure. That's just how NumPy like differentiates between rows and columns. So 0 in this case means columns, and row, like if we had set 1, if we had set 1, then we would get the average across each of the different rows, because that's just like, that's why the axis parameter is there, to allow us to make a choice about which way we want to take the mean. It's possible in NumPy to have 3-dimensional arrays, 4-dimensional arrays, and so on, and then you could set the axis parameter accordingly. But
I got that. Thank you. And
yeah.
But my second question, when we're defining features, why do we just subtract iris features from iris mean? what is the intuition of that again? I'm thinking you might have said it, but I missed it.
Yeah, sure. So we want to center the data, like that's our goal.
Okay.
So the intuition, so what that means is just taking the mean of each column and then subtracting it from each of the elements. So that way now the mean of like our features, the mean for each column is now 0, as opposed to 5.84, 3.05, whatever. So like that's what we want to do. Like in our heads, we want to subtract the mean, and then it turns out that the code to do that is just as straightforward as literally subtracting the mean from the features.
But we want to subtract the mean for what purpose? Like what? Maybe I just have to reread this question. I haven't watched the PCA lecture yet.
Oh yeah. That's
okay.
Yeah, that would make sense then. Because in the lecture, there's an example where we, if we don't center the data, then all of our rank 1 approximation, or if we have a rank 1 approximation, then it might be drastically far off from like the actual data.
Okay.
So, because it's guaranteed to go through the origin, is like the rank 1 approximation. So that's why we center our data, so that way our data goes through the origin to begin with.
Okay.
And yeah, there's just generally, yeah.
Thank you.
Yeah. There's a question in here about, is there a reason why we don't normalize it too? I think Yolanda answers it perfectly. Yeah, we can. Perhaps we probably should. But there's no, we just don't bother to do it in this lab. I will push back and say that there are some cases where it does help you. For example, when you're looking at, you're trying to figure out what factors in, what columns influence the different principal components. If we had a column that was on a completely drastically different scale than all of our other columns, then that would have a disproportionate impact on the different principal components, and our analysis would say, oh, this column is super important because it accounts for almost all of the variance, when really it's just on a much larger scale. So that's one reason why we might normalize. In this case, all of our features are already on roughly the same scale, and we're not going to that level of analysis anyway, so it doesn't really matter. So isn't it necessary for any form? Yeah. It's not strictly necessary, especially for this lab, where we're just kind of going through basics of PCA. But yes, if you want to actually make conclusions based off PCA, or if you want to actually interpret the results of PCA, yes, it is better to normalize things. But in this one, we're literally just walking through the steps. So it's not super important in this case. But yes, good point, Neil. So I guess that's question 2A. We've centered our data. That's all we've done. We haven't normalized it for whatever reasons. So it says, as you may recall from lecture, this is question 2B, PCA is a specific application of singular value decomposition. In the following cell, let's use np.linalg, whatever, to compute the SVD of our features. Store the left singular vectors, the singular values, and right singular vectors in these values. So I think actually in the lab, the blank lab, it's just this. But hint, we're going to want to assign 3 things. So I guess first we can just take a look at what np.linalg.svd returns. So we want to call it on our features. Oops. Yeah, we just want to call it on the features that we defined before. And it says use full matrices of false. So don't ask me why we have to set full matrices equal to false. I think it's just a NumPy, just like a NumPy thing. But to get the proper results of SVD that we use in this class, we have to set full matrices equal to false. So if we do that, it looks like we get one big array here. We can keep scrolling down. Oh, and then we see two other arrays. So we have three big different arrays here. Surprise, surprise, these correspond to US and VT, or U sigma and VT, which we call sigma S here. So what we can do is we can literally just do this. Just call SVD on our features, make sure to set full matrices equal to false. And there you go. And then the little output here is, it just shows like the different dimensions of U and VT, and then what our singular values are. So U is a 150 by 4 matrix. That makes sense. Our original data has 150 rows and 4 columns, so that's why U should have that shape. We have 4 singular values in S, which again, 4 columns, 4 singular values. And then V transpose is 4 by 4, because again, 4 columns, so 4 by 4 matrix. I guess we can set full matrices equal to true, just to see what happens. It looks a little bit weirder. For example, this row, it has a lot more than 4 elements. Why that is, I don't really know. But we want to set equal to false. And what do you know? We passed the test cases. Any questions about 2b? This is just feeding something into a function that they tell you to do. Okay, if not, then I guess we'll move on to 2c before hand it over to Kevin. So what can we learn from the singular values in S? So it says, first, we can compute the total variance of the data by summing the squared singular values. So I guess back to class input again. Any ideas what to put in for this line? What do I write here? It says we want to sum the squared singular values, and these are the singular values. So a couple different responses. Someone says np.sum s squared doesn't work. Someone says let's do a list comprehension. A couple other suggestions, dividing by features.shape, 1 divided by len times np.sum. So there's two different, it looks like there's two different like possible solutions here. The first one is to just do np.sum s squared. Oops, not sp.sum. And right, it doesn't give you the exact correct value. It doesn't, in fact, it doesn't get you anywhere near this value. If we sum up all the singular values, we get 681. The feature variances sum up to 4.5. So clearly something is wrong here. And yes, that's what other people have suggested. We want to divide by the length, by the overall length, basically the number of different data points that we have. So if you wanted to, you could just hard code it. It's 150, and then you see 4.52 is equal to 4.52. But there are some other ways you could do it. I think Kevin suggests features.shape 0, and that would work just fine. The length of U would also be a good thing. But yes, we need to divide by the total, basically the number of data points that we have. And I think, again, this question is a little misleading because we say, oh, just calculate the total variance. You don't have to divide by anything. Well, the reason why you do is because these squared singular values, this equals like the sum of the squared deviations. And if you remember the formula for variance, we basically say if we have like a list X, we just sum xi minus x bar squared. We sum that for all the different xi's, and then we divide by n. If we don't divide by n, then we just get the sum of squares. But we divide by n to get the variance. And so if we just sum up all the different s squared, then we get the sum of squares, and then we have to divide by n to get the variance. So that's one way to kind of rationalize it. I'm not too sure about the exact like mathy derivation behind this. I'm pretty sure it might be. I'm pretty sure that's in discussion. But yeah, you have to divide by the length of u, features.shape 0, just 150, whatever it is. And then again, we pass the test cases. Any last thoughts on anything question 2 before I hand it off? All right. Well, if not, or I guess if so, you can just ask it in the chat and I'll be active in the chat. But if not, Kevin, let me make you co-host. Make co-host. Are you good to screen share now, Kevin?
Yep.
All right, sounds good. I guess I'll stop.
Okay. So let's move on to A, where now we want to project our data, which is in 4 features, down to 2. So in general, right, data that's even in 3 dimensions, it's sort of hard to visualize because like you get a cloud of points. And when you have data in really high dimensions with a ton of features, it gets really, really hard to visualize and like display. And this is one of the big things PCA is useful for. We can reduce our dimensionality of our data to 2 dimensions or even 1 dimension so that we can plot it easily. So that's what we want to do in this question. We want to multiply features by our first 2 principal direction vectors, right? By our first 2 right singular vectors in V. So the vectors that give the directions of our principal component, or basically the axes, they're going to be represented by the first 2 columns in V, or the first 2 rows in VT, or V transposed. So how can we get the first 2 rows in VT and now turn them into column vectors and multiply that by our features? That would give us a 150 by 2 matrix, which represents data reduced to 2 dimensions. Iris 2D equals features. Okay, good. So basically, we have iris 2D is equal to features. We multiply this with at. This is basically matrix multiplication. We take the first 2 rows of VT, which correspond to our 2 principal vectors. We, of course, want all the columns. And once we transpose that, this will basically give us the correct shape that we want, basically a 4 by 2 shape, right? Because we want our resulting dimensionality reduction matrix to be 150 by 2. We only want 2 dimensions. So this would give us this, and I'll test pass. Just to visualize what this would look like, this is basically a 4 by 2 matrix. Right? This would be the first principal component vector. This would be the second, PC1, PC2. Okay. So let's move on to plotting this. Now we can see exactly why PCA is so useful. Notice that we have sort of a splitting up of each of the three classes with each point. Each point here has a PC1 and a PC2 value, a principal, like it has two principal component values that we plot. And points in one class should have a similar PC1 and PC2 than points in another class, as you can see by this split here, right? We can see that there's sort of this barrier between blue, which is Setosa, orange, which is versicolor, and green, which is virginica. So yeah, that's one of the purposes of dimensionality reduction. When we plot it, it'll actually give us these nice little groups that are separated. So what do we notice about the plot above? I kind of gave a little bit away, but what else do you notice that I haven't mentioned? So one of the things that I did mention was that we have separation of classes, right? However, what else do we notice as well? Is this a perfect separation? Does this perfectly like separate out all the? No, it is not perfect, right? We still see some overlap between versicolor and virginica, right? So PCA, at least in this form, or in this two dimension representation, it doesn't always give you this perfect split, right? And that'll go for any like that'll go for any classification sort of technique that tries to split up categorical variables. Like you won't always get this perfect split, but it's pretty good. There's some overlap, but it's pretty good. So still some overlap in versicolor. I'll just say in green and orange. Let's type that stuff out. Okay, so now on to question 3C. Now, what proportion of the total variance, I mean the total variance between all of our observations, all of these scatter plots, all of these points, like the total variation, total variance for all of these points, when we project it down to this XY axis, this PCA plot, what proportion, like we still like wanted to, the point of PCA was we wanted to keep the principal component vectors that kept the most variance in the original data points, right? We wanted to make it such that the variance would be large enough such that this class separation would actually still show up. So now we want to calculate what proportion we still kept, because we still lost some variance. Obviously, reducing dimensionality is going to lose a little bit of variance, right? Because we're really just chopping off some vectors that represent the entirety of the variance. So remember that the singular values, the values in the S, like the values in the S array that was returned by SVD, does anyone know what those represent? Right. The individual PC variances. Well, it's actually the square root of those PC variances. It actually has to do with things called eigenvalues, which is not important for this course, but the important thing is to get the variance, we actually need to square these values. So in order to, yeah, but basically they still represent the variance like by a certain principal component. So principal component vector. So, which is basically the variance among like a certain feature. So when we project the data down to 2 dimensions, we just basically want to square everything, sum it, and divide by the total variance. How can we implement that in code? Exactly. We would first take the sum of the first two, or the, what is it? Basically our first two singular values squared. Or actually, this would represent our singular values. And we sum that up. We need to like scale it by the length of our features, right? Because we have to, this is just part of the process of total variance. We must scale it. And we have to also divide that by our total variance, which we already calculated, right? That would give us past test case. Yeah. Square the first two singular values, sum them, scale them, and then divide by the total variance to get the proportion of total variance. So this is a useful sort of formula to just write on your cheat sheet, because proportion of total variance is an important concept. We want to know how much we've lost. And as you can see, the first two principal components actually keep almost all of the variance that we had in our original data set. 98%. We need to scale, because if we don't, basically we have this, we just get some variance that we need to scale it such that we want to, like in this question, we want a proportion of the total variance. So we need to account for like when we calculate like the sum of these variances, we have to have like a scaled value. So like when we divide by, like we want to make sure that it can't be larger than our total variance, because the sum of these variances have to be less than the total. So features.shape. No, like if we want like the total variance, we wouldn't need to scale this, but in this case we do. Okay, so that passes. Yeah. Okay, so now that we know that the first two principal components keep most of the variance in the original data set, let's now try to just plot each of the variances that are represented, or the weight of each principal component, with a scree plot. The reason it's called a scree plot is because like a scree is like it's this geographical thing where it's like a hill, but it's like flat, and then it's a super sharp thing at the bottom. But yeah, how can we make a scree plot to show like the variance for each principal component? So how would we go about making this? How do we start? I'll just fill some of this out for you. Of course, we want to plt.plot, 1 to 5. We want to square S and divide by the number of features. Good. All right, because again, we need to scale. So yeah, again, we're getting the average. So we would need to divide by 150. So let's see what just happens. I'll just copy and paste this in plt.plot. Instead, to just generalize, I will change this to features, or iris features, which is the same as features. Shape 0, right? Because that'll give us 150. We could also just do length of iris features. Doesn't matter. And hey, that gives us what we want. And of course, if you want to match this graph exactly, we want to do our X labels. Let's actually do this before. Principal component theta and y label, variance, component scores. Oh, cool. Oh yeah, I guess we can title it if we want to. But yeah, basically that concludes question 4. Are there any other questions about how exactly this stuff works? This is replot components. Cool. That gives us a nice looking graph. Okay. Yeah, Isaac is right. Oh yeah, Isaac's right. We get the average square deviations instead of the sum. So we need to divide by the total number of observations we have. Okay. Any other questions? And oh yeah, let's run greater than check all. We have our own pass.
Could you go back to question 1?